In the last class, we looked at the solar energy in the context of a transaction between sun and earth. So, we saw the sun to earth transaction. Basically, we were looking at the idea that the sun puts out so much of energy every second. So, that is like a powerful equivalent of conceptually equivalent of a powerful bulb in the middle of the solar system, and from there energy travels all over in all the directions equally, and then some of it reaches the earth. So, we looked at that process, we looked at several parameters that are involved in that calculation, and we arrived at some number of how much energy arrives per second to the planet earth. So, that was what we did in the last class. In this class what we will look at is the next step. So, since that once that energy arrives at the outskirts of our planet, what happens to that energy? So, where does it go, how does it get distributed, and then what happens to it eventually, right. So, all that energy has arrived, what is happening to it eventually in the planet is what we are going to look at, where is it getting distributed, what is being done with it, and so on. So, that is what I am referring to as the solar energy budget. How are what are the various places in which this is getting distributed. So, you can think of it notionally as some kind of a equivalent of a budget. You put different quantities into different parameters, and then see how the total gets distributed into all of these things. So, that is what we will look at in this class. So, what are our learning objectives? So, our learning objectives are these: to know how incoming solar energy is distributed across various phenomena on earth. Okay. So, different phenomena that are there, natural phenomena on the earth, where is the solar energy getting distributed. So, that is number 1. And number 2 and number 3 are sort of related, but in any case they are two separate aspects. First is to become aware of geographical and seasonal aspects associated with solar energy. Okay. So, what are those concepts, geographical aspects and seasonal aspects associated with solar energy. So, that is something that we will look at. And finally, we would also like to become aware of the impact of time of day on our ability to receive solar energy at any given location. So, where we are, what is the intensity of the solar energy that we are receiving at that point in time, how is that affected by the time of day. So, these three are our learning objectives for this class. So, as we go through various concepts through the class, these are the points that I will try to highlight as we go through it. Right. So, we sort of saw this in one of our earlier classes, the various layers of the atmosphere. So, and perhaps the thing that is of relevance to us is just to keep in mind that 80% of the mass of the earth's atmosphere is in this lowest section called the troposphere, and essentially all our commercial activity, commercial air activity, everything sort of happens here, and beyond that you do have all these other regions, and in fact we are doing some let us say satellite related activity in that region and so on. So, it is not that we do not use these things or that they are irrelevant to us, but 80% of the mass of the earth's atmosphere is in the troposphere, and at least so we need to be aware of it. So, naturally correspondingly many more phenomena tend to happen in this troposphere. So, that is something that we will keep in mind. Of course, energy that comes from the sun essentially comes through these layers. So, when we stand out there in the in the sun and we feel the heat of the sun, so that is energy from the sun that has left the sun several minutes ago. Typically I think it is about 9 minutes or something that it leaves the sun, and then it travels through space, goes through these layers of atmosphere and makes it to us, makes it to the surface of our skin, and that is how you feel the heat. So, these are all there in the pathway by the time the energy from the sun reaches you. So, this is something we will keep in the back of our mind, we will use it as we find necessary. And this is what we did last class, where we basically looked at the idea that the sun is putting out power equal to 384 iota watts. So, it is like a very powerful bulb, you can think of it that way, in the middle of the solar system, which is lighting up the whole solar system. That light gets radiated in all different directions, and then some of it arrives at the earth. So, that is basically what we saw, and we ran the calculation of as it goes away from the sun, how effectively, because it is getting distributed over a larger and larger surface area, the intensity, that is the energy per unit area, is decreasing, or the power per unit area is decreasing, and so there is a certain power per unit area that arrives at the surface of the earth, and that value we calculated to being about 1.755 into 10 power 17 watts or joules per second. Okay. So, that is what is arriving on the earth from the sun after it has travelled the entire distance that it has to travel between the the sun and the orbit of the earth. Okay. So, this is 1.755 into 10 power 17 watts, or it is about roughly 175 into 10 power 15 watts, or we would refer to that as 175 petawatts. So, 175 petawatts. And again, if you have any doubt, you please look at our quantities that we saw in our first class on the scale of quantities, and this is the kind of number that we are dealing with. So, this is the energy that comes to the outer reaches of the Earth's atmosphere. So, that is where it is arrived. So, now in this class we start from there and we see how this energy penetrates into the earth and what is happening as the process proceeds, right. So, we have here you can think of this as this is the sun, and 175 petawatts has arrived at the outer reaches of our atmosphere. So, we have the atmosphere and down below we have earth, the solid ground of earth. So, what happens, as you will see through this process, is that as the sun's energy arrives at the earth and begins to penetrate the atmosphere, it gets to participate in a number of different phenomena, and so some of that energy gets used for all of these phenomena. So, that is the process that we will see as we proceed through this stage by stage. Okay, so, out of this 175 petawatts, as it penetrates the atmosphere, we find that right at the top, so in the top layers of the atmosphere itself, you have about 6% that is just getting reflected by the atmosphere. So, this simply means it just reflects 6% of the sunlight coming into the planet is just getting reflected off, right. So, so that never even reaches into the interiors of our atmosphere, it just goes off the top from the outer reaches of our atmosphere, it is just getting reflected and it is on its way out. 16% is absorbed by the atmosphere. Okay. So, 16% is getting absorbed by the atmosphere, and so this can be used for variety of different things, but it is basically there in the system. So, if you see the overall process, we have to account for the 16% somewhere. This 6% that did not reach earth and simply basically bounced off the atmosphere is not something that we need to account for in any great sense, in the sense that we do not have to worry about what it can do in terms of heating up earth or cooling down earth, etc. So, because it does not participate in anything that is happening on the earth, it is just on its way out. But this other 16% is there somewhere in our atmosphere. So, it has arrived, it is sitting somewhere in our atmosphere. So, that is something we have to keep in mind. If you take this a step further and you try to see what is happening after these two processes have happened. So, there is already, you have removed 6 plus 16, 22% of what was coming in. So, you have 78% remaining, 78% of 175 petawatts that started out at the outer reaches of our atmosphere is still remaining now. So, that is 70%, 78% is still remaining. Out of that 78%, a further 20% is being reflected by clouds. Okay. So, as I said, the original 16% is being reflected by the atmosphere itself. It is the various layers of the atmosphere, just the fact that it has some material in it, it has air in it, it has air molecules in it, it may even have some fine dust in it, lot of different things may be there. In the end, that is bouncing light off of the atmosphere. But 20% is being reflected off the clouds. So, that is quite significant. In fact, this is actually quite important to keep in mind, because this reflection actually plays a critical role in temperature control. If this reflection were not there, all of this energy would still be coming into the earth, right. So, and then correspondingly this is energy that we would have to deal with inside the planet. So, it means it is going to heat things up further. So, that is something that we have to keep in mind, and 20% reflection is actually quite significant. If you ever travel by flight and you are on flying over a layer of clouds. So, you cross the layer of clouds, you are just above the layer of clouds and you are flying. If you look out and you see the clouds, it is quite glaring. The sunlight that reflects off the clouds is quite glaring and quite blinding, and it can affect your eyes quite a bit. If you just watch for a little while and you look away, you can feel the darkness in your eyes. I mean, because it's just been overwhelmed by the amount of light coming from the reflected light from the clouds. This is just even for a few, several seconds you look out the window and you watch that glaring light getting reflected off the clouds, you get that sense that it is too harsh for you. So, you tend to look away. So, that is a significant amount of light that is being reflected. Incidentally, the same thing happens even if you go to regions that are receiving a lot of snow. So, of course, when there is snowfall, you have it's overcast kind of condition through which the snow is coming. So, it looks all gloomy like you would have on a heavy rainy day kind of thing. So, but once the snow is on the ground and let us say the sky clears after that, you have this really bright blinding sunlight that you experience when you step out during the day, because there is so much sunlight that is getting reflected from that snow. In fact, people who live in these extremely snowy regions where let us say they are living in Alaska or Greenland or Iceland, places like that where there is significant amount of snow for significant periods of time in the year, they have to necessarily wear what we would call cooling glasses or some sunglasses of different kinds, which basically are some coated glasses which reflect a significant amount of the light away. Otherwise, the light is simply too harsh for the eye. Many places there is in fact there is a specific term for it. There is a term which is referred to as snow blindness. So, people who are in such regions, if they do not take appropriate care to protect their eyes can become blind simply because of an overdose of light into their eyes. Just the way people can become deaf if they have excessive sound going into their ear all the time, people can go blind if they have excessive light going into their eye all the time. Okay. So, snow blindness is something that people have to deal with if they live in regions where there is considerable amount of snow. So, that leaves us with one very interesting question, given that this is an aspect that we should be aware of. How did people who lived in snowy regions manage in early days, in the sense when before they had cooling glasses available to them? Okay, so that is a question you keep in mind. We will briefly address it towards the end of the class. Think about it. People who lived in cold regions which had lot of snow had to deal with snow blindness, had to deal with the fact that there was extremely harsh sunlight coming to their eyes all the time, so they had to protect their eyes from it, and in fact they could not really see. I mean, it would really hurt their eyes to see anything. So, they had to do something equivalent of cooling glasses to or sunglasses to help themselves see, which you may not be completely familiar with. So, you need to think about it as to what they did to protect their eye, and we will discuss the answer to that towards the end of the class. But in any case, this reflection is a very critical aspect that we have to keep in mind. In fact, this reflection is a very important aspect even from an overall planet's perspective. Of course, this is already in the planet's perspective that we are looking at. Significant amount of reflection actually happens off of the ice that is there in the polar regions. Okay, so, that also actually helps control the temperature of the planet. A significant amount of heat bounces off that, significant amount of sunlight incoming radiation just bounces off these huge ice caps that are around, and that decreases the amount of heat that is penetrating and staying in the planet from the sun. Okay. So, these are all important things. So, what we are doing now is looking at what is the planet actually doing with the sunlight that is coming in, and trying to get a sense for it, because we need to understand if we are doing something that is disturbing this, then we need to be careful, because we may abruptly disrupt this equation of how the energy that is arriving from the sun is being handled by the planet. Okay. So, that is one aspect of it. The other aspect is we are actually trying to see in this context how are we going to use the solar energy, how much of this energy is actually available for us to use, and so on. So, these are 2-3 aspects that I will touch upon as we go through with this class. So, anyway, 20% of the sunlight is being reflected by clouds and 3% is actually being absorbed by the clouds. 20% reflected by the clouds and 3% absorbed by the clouds. So, so the clouds play a significant role. So, in handling the sunlight in some form, either reflecting it or absorbing it and holding that heat. So, we will keep that in mind and then we will proceed further. So, once so at this point we have if you look at what all has been accounted for out of the 100% that arrived at the or whatever arrived at the top surface of our planet, of our the atmosphere of our planet, which was 175 petawatts, we already removed 6%, in the sense the planet did not receive 6% because it got reflected by the atmosphere. 16% got absorbed by the atmosphere, so that already accounts for 22%. A further 20% is being reflected by the clouds. So that means now 42% is basically not there, and then you also have 3% that has been absorbed by the clouds. So that is 45%. So 45% of the incoming radiation has been dealt with by these 4 phenomena, right. 6 plus 16 22, 22 plus 20 is 42, and then 3 is 45. 45% of the incoming radiation has already been dealt with simply by the atmosphere and by the clouds. Then we come further down and we find that the surface of the earth is also reflecting some of the radiation. That is why we are able to see it, right. We are able to see because light reflects off the ground, and that is why we are able to see it. So 4% of the sunlight that reaches the earth is reflected by the earth, the surface of the earth. So the land, whether it is green grass fields or buildings or land or whatever it is that is out there, is all reflecting some sunlight, and some of the sunlight just gets reflected right back. Okay, so that is 4%. So if you take all of these into account, we actually have removed 49% of the radiation that has come in. So that is 6 22, so that is 6 22, 42, 45, 49. So 49% of the radiation has been accounted for as radiation that has actually that has participated in different phenomena on the relative to the our atmosphere and earth. So if that is 49%, that leaves us with 51% of whatever is that radiation that came from the sun, and that 51% is absorbed by land and water. So every day the sunlight that comes from the sun to the earth, 50% of it or little over 50%, 51% of it arrives at the surface of the planet, which is the surface that we are standing on at ground level or the sea level, mean sea level, and that energy is being absorbed by the land as well as the water as the sunlight falls on it. Okay, so when we set up solar panels etc. on or you do any other solar device that is that you are trying to create and use, to the extent that those devices are sitting on the surface of the planet, they are dealing with this 51% that is reaching the reaching those devices. In general, of course, if you take if you remove just what has been reflected, which is the 6%, the 20% and the 4%, that is about 30% that got reflected. So actually 70% is still somewhere in the system, 70% is still sitting somewhere in the system in the form of heat. It may not be direct sunlight, but it may be heat that is present in the atmosphere and the heat that is present in the land, present in the water. So that heat is also still there. So that heat can overall also be used. If you only the reflected stuff is actually just reflected and is not really participated in anything at the moment for in the grand scheme of things. So you still have 70% available from that perspective. If you are just looking at sunlight that is reaching the surface, then that is 50%, 51%. It is being absorbed both by the land as well as by the water. And so what would happen? So now supposing this is all that happens, right? Supposing this is all that happens, every day you have all this happening, and let us say this is all that happens, then every day you have 51% of whatever is coming in staying on the planet, right. So if that keeps staying, every day you are adding heat to the planet, and so then the heat should keep on rising, right. So temperature of the planet should just keep on rising every day. We do not see that, that is not what happens. We see that on average the planet maintains some temperature, right. We have seasonal variation, of course we have seasonal variation, we have summer, we have winter, we have spring, we have autumn, all those things we have, but basically there is seasonal variation, but in principle we are anticipating that the temperatures will be roughly the same across the, once you know which season it is, you can compare it with the same season last year, same date last year, and get a reasonable idea of how the temperatures are holding. So this is always our expectation. So which means the heat is not just collecting on the earth indefinitely. So this 51%, which is half the power that is landing upon earth, which shows up on the land and the water and gets absorbed by the land and the water, is actually being something is happening to it, right. It is not just staying there. If it stays there, it will heat the planet. So it is not just staying there. So what is happening to it? So those are a few of the phenomena that take care of that heat or utilize that heat, I should say, are what we are going to see in the next few variations or developments of what you are seeing on your screen. So out of this 51%, 45%, a very large fraction of it, 45% is used for air that is rising, which basically means it heats the air, right. So, air close to the surface of the land as well as close to the surface of the sea gets heated up because of the heat that has been absorbed by the land and by the sea, right. So, first land and sea absorb the heat and they have lot of heat available in them. That heat is used to heat the air, that is just the layers of air that are very close to the surface of the land as well as close to the surface of the water. So, when that heats up, you have hot air that is beginning to move up and cold air from above in the atmosphere that begins to come down. So, that is typical convection that is going on, and that is how our entire weather system works. You have hot air and cold air that is mixing all the time, hot items are moving up and cold items are coming down, and there is a lot of mixing that is going on, and that is how essentially much of our weather phenomena begins to happen because of this fundamental set of activities that are happening. So, 45% of the heat that first got absorbed by the land and the water gets used for a few different things. One of them is this rising air, it heats the air and then it begins to rise. The second very important thing is cloud formation. So, all the clouds that we see, including those clouds that are reflecting the sunlight, those clouds are formed due to evaporation of water, right. So, water from our rivers, from our seas, from various places, wherever it is evaporating, all the time it is evaporating. It is evaporating because of the sunlight that is falling on those areas of that are containing that water, right. So, when that happens, for evaporation to happen, you have to provide the latent heat to enable that evaporation to happen, and so that is how the evaporation process is happening and cloud formation is happening. So, every time you see a cloud up in the sky, you know that some energy has been absorbed in the formation of that cloud, right. So, sunlight that came in got utilized to create that cloud. If absolutely no sunlight was there, if there is basically a cold, then in that case we would have absolutely no heat, then it would be a cold planet, and then you are really not having any scope for cloud formation unless there is some other source of heat which may be coming from underground, but other than that you essentially do not have any other scope for cloud formation. So, solar energy is very critical for cloud formation on the planet, and so that is one of the places where the energy that has been absorbed by the land as well as the water is being used. And finally, there is this idea of radiation, which is again absorbed by the atmosphere. So, what this means is the land as well as water they also radiate out heat. Okay. So, what do we mean by that? Well, we will discuss that in just a moment, but just take it for the moment that they radiate out heat, and that radiated out heat is again absorbed by the atmosphere. It is like another source of heat. So, it received heat, it picked up that heat. So, the land, let us take the example of land, it received heat from the sunlight, it became hot, and because it is hot, it is also able to give out some heat, and that giving out of that heat is in the form of radiation, and that is that radiation has to again travel through the atmosphere, and as it travels back through the atmosphere, it can again get absorbed by the atmosphere. Just the way the sunlight that was coming in also got absorbed by some parts of the atmosphere, the radiation that is coming back from the earth can also get absorbed by the atmosphere, right. So, that happens, and all of this then eventually gets radiated back to space. So, what are all of those things? You had 45%, which is rising cloud, rising air, cloud formation, radiation absorbed by atmosphere, etc. They all contribute to this energy, and then the whatever got absorbed by the clouds also arrives here, and whatever got absorbed by the rest of the atmosphere also arrives here. So, you have 45 plus 3, 48, 48%, and then another 16%. So, that is 64%. So, 64% gets radiated to space by atmosphere and clouds. So, everything comes to the land and water gets absorbed by the land and the water. I mean, whatever comes to the land and water gets absorbed there, except for the percentage of 4% that is reflected back, and then it transfers the heat back to the atmosphere as well as the clouds, and then from the atmosphere and the clouds it goes back into space. So, 64% is radiated back to space by the atmosphere and the clouds, and there is also a small percentage which is remaining here, which is about 6%, that is getting directly radiated by the earth to space. The difference between what I am referring to here and what I am referring to here is the fact that this radiation here is going straight into space. It is not getting absorbed by the atmosphere, it is going straight into space and going out. But some of the radiation is actually first getting out of the land, getting into the atmosphere, getting absorbed by the atmosphere, and then again being radiated out by the atmosphere. So, it is just like a two stage process, whereas what is happening here is a single stage process, it just goes straight out. Okay, so this is if you take this total 6% here and 64% here, that is 70%, and we already saw that what was reflected was the remaining 30%. So, that is your 6% here, 20% here and 4% here. So, already 70%, I mean 30% just got reflected. So, we only have to account for the remaining 70%, and the remaining 70% we are accounting for here. 64% is getting radiated to space by atmosphere and clouds, and 6% is getting radiated to space directly from earth to the space. So, this is what is happening. Okay. So, now I will also add a couple more details before I talk a little bit more about this whole idea of radiation, but and that is simply that, you know, although I have stated all this in front of you, why should why should we you know, have things being absorbed by the earth, why should we have things being radiated by the earth, and what are the circumstances that are permitting these phenomena to happen. So, quite simply, whatever you saw here, which is the incoming part of the process, is all essentially happening during the day. Okay, so, it is essentially happening during the day. You have continuously sunlight that is coming in, and that sunlight is doing all of these things. It is getting reflected, it is getting absorbed, it is heating the land, it is heating the water, it is creating the clouds, it is creating you know, weather patterns, lot of things are happening during the day due to the incoming solar radiation. And then you look at the essentially the situation in the night. So, when we are not facing the sun, the side of the earth which is not facing the sun now has an opportunity to release this energy back into space. Okay, so, and that is how the radiation process happens. Okay, so, it just radiates everything back into space and it continues. So, I mean you can sort of think of it in that sense that, you know, in one case you are in a position to put out the radiation, and so that is happening, and in other case the radiation is just continuously coming in. So, this is essentially what is happening. And when we talk of radiation, it has got basically to do with the idea that any body that has a particular temperature will give out radiation consistent with respect to the temperature. Okay. So, the sun has a high temperature, and because of all the nuclear reactions that are going on there, it has a temperature internally because of those nuclear reactions, and as a result of that it keeps on giving out radiation, which is basically electromagnetic waves. And light that we see, visible light, is part of that electromagnetic spectrum, but it actually has a wide spectrum. There is a wider spectrum through which you can give out radiation, and the spectrum simply means different wavelengths, wide range of wavelengths. Some of those wavelengths we can see, and that forms the visible spectrum, and we will talk about the visible spectrum. Essentially, I think in our next class we will be spending time on the visible spectrum, but the radiation is what is coming off the sun. Okay, so, it is coming off the sun. And you have a wide range of wavelengths over which this radiation is coming out, and there is a lot of different intensities for each of those radiations. So, there is a spectrum, that is called a spectrum, what wavelength and what intensity is coming at that wavelength. So, that is the spectrum. So, that is how the radiation comes off. Electromagnetic waves leave any body that is at some finite temperature. Even our own body gives out electromagnetic radiation, except that the frequency range at which it gives out that radiation is in the infrared region of the spectrum. That is why you know, when you go look at military applications, in military applications they use these you know, infrared goggles, IR goggles, which allow them to see in the night, right. In the night, how do they see? They see anything that you see is because some radiation coming off of that body is reaching your eye, and you are able to recognize that radiation. Okay. So, during the day, visible light is falling on some object, getting reflected from that object and reaches your eye. That is how you are able to see that object. In the night, if the lights are off, you are not, there is no light reflecting off of a person who is standing in front of you, and so nothing is reaching your eye. Visible light is not coming from that person and or any object that is in front of you, and therefore you are not able to see it. But if it is a human being, they are standing there and they have some body temperature, right. So, that body temperature corresponds to radiation in the infrared spectrum. And so, if you have a glass that is sensitive to that radiation, it will convert that to an image that you can now see in your eye, okay, with your eye. So, that is how infrared goggles are made, which are used for seeing in the night vision. So, the point being, a body at any temperature is giving out radiation. So, similarly, when the earth gets heated through the sun, it also is in a position to give out radiation when it sees temperatures which are less than its own temperature. Okay. So, in the night, it is seeing the dark side of the space, and at that time the temperatures on the dark side of the space are much lower than the temperature of the earth, and so the radiation now goes off the earth, and then it is able to send off the radiation. During the day it is facing the sun, so it is facing an atmosphere that is hotter than itself, so radiation is coming into it. Okay, so that is sort of the way you have to think about it. And so when we talk of radiation here, that is basically what we mean in this entire diagram. Wherever we talk of radiation, that is basically what we mean. The idea that a body at some temperature will give out electromagnetic waves that are consistent with that temperature, and that set of electromagnetic waves are being referred to as this radiation, and that is why even solar energy that comes to us is referred to as solar radiation. So what you see here is a range of phenomena that are occurring on the planet which correspond to this sunlight that is coming in and how it is distributed through the planet and how it leaves the planet. So some few general aspects associated with this that we should sort of be better aware of because it impacts the overall picture of what is happening here, is that this is a very delicate balance. Okay. So we now saw how all the numbers add up to 100%. Supposing for some reason any one of these is disturbed slightly, let us say whatever is the amount of energy that is leaving the earth is not 100%, but it is 99.5%. So you have 100% energy coming in, only 99.5% is going out. Then that 0.5% is just collecting steadily in the system, and then it keeps heating up the system, and that is how the temperature of the planet begins to rise, right. So it is critical to keep in mind that this is a I mean it is a continuous process. Every day we are receiving light from the sun, and in fact some side of the planet is essentially receiving sunlight all the time. I mean at any given point in time there is at least one side of the planet that is always receiving sunlight. So we are continuously getting energy from the sun, and the system, the planet is in a very delicate situation because whatever we consider as our habitable conditions, it seems to have worked out just right for us. I mean in the sense those we are now in exactly those conditions. Even when we go from say the equator to the north pole or towards the north pole, we find that the conditions change so significantly, right. So and that is not a huge distance. If you take the relative distance of earth to the sun, which is 149 million kilometers, this is nothing. We are just moving about 6,300 kilometers, that is it. We are moving 6,300 kilometers away from the point that is closest to the sun to the point that is towards the pole. That is the distance. The radius is how far we move away in the direction of the sunlight. Just that makes the difference between a desert and a huge amount of snow. So that is a very delicate balance. We are just at the right region where you have ice at one end, you have a desert at the center, and then in the middle you have all these rivers that are flowing. So that is a very delicate range of temperatures over which the planet is sitting, and this range seems to have worked out very conveniently or worked out in a manner that is appropriate for life as we know it. And so the life that has evolved on the planet has evolved with this range of activities being present on the planet. So anything that we do that disturbs this has potential to have many ramifications. So that is why there is so much concern about CO2 in the atmosphere, because if you have a slightly higher CO2 in the atmosphere, the manner in which this balance of how much energy comes in and how much energy goes out is altered slightly as you slightly increase the amount of CO2. And as you can see, we are not just slightly increasing the amount of CO2, we are increasing it in ways where in the matter of 80 years you can double the amount of CO2. So when you do that, the balance is actually being twisted quite significantly, and it is not just one parameter that gets affected. That is the point that you have to remember. Every time one parameter gets affected, many other parameters get affected, and they build on each other. That is a much more dangerous problem. So for example, as I said, even if it is just a tiny fraction extra CO2, and let us say that leads to a slight increase in temperature, we are already seeing temperatures going up by a degree or two, right, across the 100 years. Expectation is another degree or so it will climb up. When that happens, you will see melting of ice, and many places where that the region over which that ice is there will now shrink, because there is a region which is the boundary. That boundary is where the 0 degree centigrade is between much below 0 degree centigrade, and then the heat goes up as you come from the pole towards the equator. So, there is a boundary where the natural temperature is hovering around 0 degrees centigrade. If you raise the overall temperature of the planet by 1 degree centigrade, that boundary moves closer to the poles, okay, because that means there is more area over which the heat is available, and therefore the boundary moves closer to the poles. Many things happen because of this. Just because the boundary moves, first of all the amount of water suddenly goes up, and that makes some impact in terms of how much the water encroaches into land, etc. That is one aspect of it. But another interesting aspect is that when the boundary moves closer to the poles, there is less ice present on the planet. If there is less ice present in the planet, there is less reflection of sunlight from the planet into space. If there is less reflection of sunlight from the planet to the space, more of the sunlight is sitting absorbed in the planet. Okay. So, by doing a small 1 degree difference in temperature, you have opened the gate to increase the heat of the planet in a much more significant way, right. It is a delicate balance, you are sort of sitting on a peak and you have pushed it off the peak. If you push it off the peak, there is a major run downhill. So, that is sort of the kind of situation we are dealing with, and so and that is the reason why there needs to be more care, because if you push it a little to the hotter side, you increase the chances that you are pushing it much more into the hotter side, because you are adding factors that were not related to this directly. You suddenly melted the ice, because the ice melted you reduce the amount of reflection, because the amount of reflection got reduced, you are increasing the amount of heat even further. So, this is the kind of issue that is there in this balance, and that is why this balance is so critical, so important for us to be so alert to what this balance is. Okay, so that is one aspect of this whole discussion that we should keep in mind. The other aspect is of course the fact that we are now trying to harness this energy. We want to harness this energy, and therefore it is essential for us to get an understanding of what is this energy that is arriving at the planet, where is it situated, so that if you want to harness it, we have an option of harnessing it, right. So, we now got a sense through this discussion so far how much of sunlight is coming, where all is it going. So, we found that 30% just gets reflected back, but still 70% is somewhere in the system, either in the form of heat in the atmosphere, or in the form of heat in the land, form of heat in the water, and then this is again also getting radiated, forms clouds, lot of things are happening, but there is a lot of scope for us to capture this energy. And even with 70% of heat arriving of the heat that comes at the top part of our atmosphere, if only 70% of it reaches the surface of the planet, we still find, as per our calculations in the last class, that every hour we are receiving enough sunlight from the enough energy from the sun equal to everything that all of humanity uses in today's modern world for an entire year, right. And that gives us such a large room to work with and satisfy all our energy requirements using such a clean form of energy, which is solar energy. And that is why there is such an interest in it, and that is why we are spending a lot of time in trying to understand it, trying to look at devices associated with using solar energy, and we are looking at it as our first and most prominent non-conventional source of energy. Okay, so we looked at the how it is distributed as you come from the top of the atmosphere, top reaches of the atmosphere down to the surface of the planet. Now, our planet, as we are aware, is essentially nearly spherical in shape, and I also just described to you how the temperature varies as you move from one region to the other in the planet. So, let's look at that also as a factor, because that gives us an idea of which are places where in the planet where there is greater scope to do something with solar energy, and what are parameters that we have to keep in mind. Okay, so what are the geographical aspects associated with this, what are the seasonal aspects associated with this. So, we now have an outline map of our world, and we find that if you look at how the solar energy comes to our planet, we find a big band here, which is where let us say we are looking at the entire geographical and seasonal aspects have got to do with what time of the year that we are talking about. So, just for discussion sake, let me just say that we are looking at March of any given year. Okay. So, March of any given year is typically a time when the northern hemisphere is coming off of winter. It has had its winter in say December, January, February, and it is just slowly coming off of winter. So, it is moving towards spring, and then eventually it is going to move towards summer. So, it is coming off of winter, whereas the southern pole is actually been in summer. Okay. So, the heat is a little more into the southern side of the hemisphere. So, that is why you see this red band actually not really centered around the equator, but actually a little towards the lower side. More of it is present towards the lower side, little less towards the northern side, more towards the southern side. So, the southern hemisphere is coming off of summer, the northern hemisphere is coming off of winter. So, but you still see this big band where there is considerable amount of sunlight that is coming down on it, fairly harsh sunlight, and you can see of course India is right here, and which means we receive even as we come off of winter, most of India receives a lot of sunlight, and we know that. We know, I mean, in India, almost anywhere in India, of course winters are quite strong in northern parts of India, quite severe at least by Indian standards in northern parts of India. We do have places where temperature drops to 0 degrees C, even in our capital. I think in winter you will have some days where temperature begins to dip close to 0 degrees C, but certainly northern, even further north if you go, temperatures dropping below 0 degrees C is not uncommon, snow is not uncommon. So, this is the range of temperatures that we have, but generally for fair part of India, at least half of India, you get a lot of sunlight, you get a lot of heat, and that is what is quite visible in this picture that we see. We also see that as we are perhaps aware, almost all of Africa gets a huge amount of heat from the sun. All of Australia gets a lot of heat. So, you have Australia here, you have Africa here, and a lot of South America. So, significant fractions of the world are receiving a lot of heat from the sun, and so these are regions, geographical regions where you can potentially have a lot of solar energy devices deployed, and you have a great chance of you are getting good quality sunlight, in other words high intensity sunlight. So, with smaller devices you can presumably capture more energy. So, the promise of solar energy is highest in these places, is what I am trying to say. It is not that it is not there in other places, but it is the highest in these places simply because of the natural position of these places relative in the geographical sense, which results in the kind of sunlight they receive at different points of time in the year. So, this is the major band, but we still have a little bit more. We have regions on either side of it which receive a little less sunlight. Maybe on average the temperatures are probably about say maybe 5 degrees or 10 degrees lower as you go away from the hotter regions towards the colder regions. So, you can think of two more bands of regions of the planet where the temperatures and therefore the amount of or rather the amount of sunlight coming and therefore the temperatures are little less because of the position of that planet and the fact that it is it is a little bit oblique, that the angle at which the sunlight is arriving at those places. So, but actually interestingly you find that many of these places, so essentially most of Europe falls in this category, right, most of Europe falls in this category. In the southern hemisphere not much, this small tips of southern America come into this category, South America. Fair bit of North America comes in this category. So, fair bit of United States, fair bit of I mean essentially all of Canada is all going to come in this category where they do not receive as much of the harsh sunlight, harsh and direct sunlight that some of the other places receive, and that does not mean that they cannot use solar energy devices. In fact, many of these places have invested a lot in using solar energy devices, and it does work for them, but they just have to accommodate for the fact that they possibly are not going to receive the same amount of same quality of intensity in their sunlight as some of the other nations which such as Africa, fair bit of South America, Australia and India are going to receive. So, but this is the other two regions, and then of course you have the two extremes here, the closer to the polar regions here, the closer to the south pole and closer to the north pole. So, those are regions which are basically in summer you are going to get some sunlight, in winter it is all going to be dark and so on, and so there again it becomes more difficult to really harness this solar energy as effectively. So, that gives you some idea that geographically also our planet has some features associated with it, and we have to deal with these features. We have to be aware of these features and we have to deal with these features. So, I was also mentioning that this delicate boundary that we have to watch, which is where that 0 degrees centigrade is, I mean mean temperature is of about 0 degrees centigrade. So, I mean just to illustrate here, maybe that if I were to use this boundary here, as that region where the temperature just about drops below 0 degree C. If the mean temperature of the planet goes up by 1 degree C, that boundary may move up. Okay, so this means all the ice in this sector will now start melting, and that is a lot of ice. I mean, that is a lot of ice. If all the oceans that side were frozen, they all start melting. So that is a dangerous situation to have, because that means also there is less amount of ice up here to do the reflection, wherever if it happens to be in the floating around in the water, etc., or even out here, it is on the land, you have ice on the land. If it is there, that may also start, you will have less, because ice on the land that is here would have melted. So these issues are there. That is basically what I was referring to. Well, before I move forward, I asked you a question earlier in the class about snow blindness, and that would affect people that would be here, and that would affect people that would be here, any of these places where you have a lot of ice. So they do not have sunglasses, they do not have what we Indians refer to as cooling glasses. So what do? They actually have essentially maybe even some leather kind of thing, or a piece of wood that is used equivalent of a sunglass, but it has very tiny slits, and because it has tiny slits, the amount of sunlight that comes in decreases drastically. It's just the same as squinting your eye and then seeing with a tiny opening of your eye, because you have closed most of your eye and you have a very tiny opening, you see only a very dim amount of light coming through to your eyes, right. But if you are stuck in a place where it is so bright, you cannot keep on walking around with your eyes half closed, it becomes difficult for you. So they have and they do not, and since they did not have the technology to make sunglasses the way we currently have them, the older form of dealing with this was simply they would have some structure which would sort of serve the same physical shape of a set of glasses, but it would just be a piece of opaque item with two tiny slits, one for each eye, so that it is a narrow slit through which you actually see. And that was a thing. It could even, like I said, be a piece of leather with two tiny slits which you could just tie around your eyes and use, and that would make a big difference in the amount of sunlight that the people were exposed to, and therefore significantly I mean alleviate this issue that they had with extremely bright sunlight. So that was a question I asked earlier, and I thought I should clarify that to you here. But in any case, with respect to this plot that we have here, this gives you an idea of what happens geographically with respect to sunlight that is arriving on our planet. And the last thing that I think I should draw your attention to is what happens as a function of time of day. Okay. So what you see here is again the planet, our planet, and we will assume that we have incoming sunlight from here, and this is the north pole. So directly we are facing down on the north pole, and so east is here and west is down here. Okay. So what you can see here is clearly this is midday, this is closer to the morning, and this is closer to the evening. So we know from our experience that in a given day, as you come towards the middle of the day, you feel the maximum heat when you are out there in summer, when you are out there outside, certainly in places like in India. In summer, if you are out there in the middle of the day, it is so harsh. Many places you have to wear some kind of a hat or a cap, or put at least some cover on your head, or you are really going to take a lot of heat on your head. And so most of us do not really enjoy being out in the sun in the middle of the day in peak summer, right. At the same time, we know that during the evening as well as during the morning, it is quite comfortable in many places, even though it may be summer. So why is that the case? That is because the same same amount of energy that is coming in is during the middle of the day is distributed over the smaller piece of area, but during the early part of the day is distributed over this larger piece of area, and similarly in the evening it is distributed over this larger piece of area. You can clearly see that this area here and this area here are much larger than this area here, right. So the same amount of energy is getting distributed over a smaller region of area, a smaller area during the middle of the day than it is during the morning or the evening. And as a result, so that is basically intensity, that is intensity. So the power in per unit area is higher during the middle of the day, it is a lot less during the morning and during the evening. So similarly, when you have a device that is trying to capture solar energy, generally if you do nothing with the device, if you just leave the device in the best possible condition, in one single condition, which is whatever is the best data that you got from it in all your tests, you leave it in that condition undisturbed, it will gather the best sunlight during the middle of the day. It will gather less during the evening and gather less during the morning. So, so that is another aspect that we have to keep in mind. So, in fact they even call it IAM or incidence angle modifier. We will discuss this more later. Incidence angle modifier, it simply takes into account the idea that when the light is perpendicularly falling on the device, it is in the best position to capture the solar energy, whereas during the morning as well as during the evening the light is arriving at an oblique angle as opposed to vertically down, and therefore if the device is sitting flat, if you have this light arriving at an oblique angle, it is in a less ideally situated to capture that energy. It is also less ideally situated to capture the energy during the other part of the day, either the evening or the morning. It is best situated to capture the energy when it is in the middle of the day. Of course, so they have to account for it. Basically that is the point. The point is you have to account for it. So if you want uniform energy throughout the day, you have to keep that in mind, that you are not going to get the same amount of energy by if everything else sits the same. So they have tried various ways to address it, and we will see that in some of our later classes. So they move the device. So the device is moved such that even though the sunlight is coming this way, the device also faces that way. Sunlight is vertical, it faces this way. Sunlight is coming from this direction, it faces this way. So you have to do something to address it, is the point. The point is you cannot just assume that you just put a solar device out there and it has solved all your problems. It will take care of everything, right. So that is something that we have to look at. So this is this IAM, and we will see that in greater detail in one of our later classes, but it sort of conveys to you what happens with respect to incoming sunlight and different points in the day. Okay. So we looked at three different things in this class. In conclusion, we will try to sum these three aspects together. We found that solar energy that arrives on the top of our planet ends up participating in a wide range of phenomena as it traverses through the planet. Okay. So as it comes through the planet, there are a wide range of phenomena in which through the atmosphere and reaches the surface of our planet, the wide range of phenomena in which it is participating. So we need to be aware of it so that we understand the complexity of what it is that we are dealing with. Okay. So when it comes from the sun through most of those 149 million kilometers, it is basically vacuum. There is nothing there. It is just coming in as electromagnetic radiation. So there is no real phenomena that of any great significance where it is getting absorbed in any major way. By and large, it is arriving on the planet. Once it arrives on the planet, from the outskirts of the atmosphere as it traverses in, lot of things are happening, and as a result of that, various aspects are happening about with respect to what is getting reflected, what is getting absorbed, what phenomena are happening in terms of cloud formation, hot air rising, weather phenomena. All these things are happening as a result of how these layers of the atmosphere are dealing with the incoming solar radiation. Okay. And whatever we have as life on the planet is very intricately related to this phenomena that is happening. The idea that there is sunlight coming, and the fact that there is this atmosphere that is interacting with this incoming radiation, and as a result many things are happening. Rain happens, clouds form, storms happen, lot of things are happening as a result of this process of the sunlight coming and interacting with the atmosphere, interacting with the land, interacting with the water. So we looked in detail about how this interaction happens and what are all the various steps involved in this interaction, and we found that there is a wide range of phenomena through which the solar energy is absorbed and something happens with respect to the solar energy, and then it is later released through a wide range of phenomena that are happening in the system. And it is important to note that these phenomena are very critical in the grand scheme of what this planet is doing in terms of its weather circumstances, in terms of its equilibrium, in terms of life on the planet. If we do anything that messes up or disturbs this set of events that are happening by either overplaying one event or underplaying some event, then we risk the chance that we are going to push the atmosphere into one direction from which it may further slide into that direction without any control, okay, or without our being able to control it. So you cannot simply say, okay, I just raised CO2 by 2%, it's okay, let us continue raising CO2 to 3 times the current value, and then we will quickly bring it down, we will find something to bring it down quickly. So, let us not worry about it. The point is when you go from whatever is the current value to 3 times the value or 2 times the value, you will trigger some other things which will push it so far into the other direction so fast that you will not have it is unlikely that you will have technologies that will urgently bring it back, circumstance to bring it back, right. So, you may even actually you may tip the scale in one direction, you may move by just going from one value of CO2 to double the value of CO2, you may tip some set of circumstances into one sequence of events, where at that point in time if you simply bring it back from the double that value to the original value, that alone will not suffice, that is the point. Okay. So, from 0.04% CO2, if you suddenly climb to 0.08% CO2, you will trigger a chain of events where you are putting yourself in a situation where at that point in time, if you bring it back from 0.08 to 0.04, that will not alone be sufficient, you will not bring all the events back to where it was original. They have started one sequence of events, just bringing that from 0.08 to 0.04 is no longer going to be sufficient for you, you have to do many more things to bring that back to some kind of a situation that you are originally comfortable with. So, that is the critical thing that we have to remember, it is not just one number that we are worried about and you can just look at it and say it is okay for another 50-60 years, we will figure out this a little later. We have the danger of triggering other events in this process. The second thing we looked at is that geographical locations and seasons are important aspects impacting solar energy received by specific locations, and this has an impact in terms of what kind of how we will go about deploying solar energy devices in those locations. We have to be aware of the fact that they have a geographical location, and as a result it has some characteristic associated with how the solar energy arrives there, how much solar energy arrives there, what is the quality of the solar energy arriving there in terms of intensity and so on. And therefore, if there is a certain power demand in that for the population, some energy demand for the population in that region, we have to account for the fact that the solar energy has a certain intensity and those devices have to be correspondingly put in sufficient numbers that with that intensity those devices will provide enough energy for that population. So, that calculation has to be taken into account, and clearly based on which region it is, for the same total population you can have a different set of solar energy devices addressing the needs of those population. So, that is the second aspect of it. And the third aspect, as I pointed out, is the fact that during different times in the day the quality of the sunlight is going to vary, and it is something that you have to address. You have to have a mechanism of addressing, you cannot assume that it is going to be the same, and that is why in many of the solar energy based applications they will always have some additional storage devices, because the best amount of energy that they are going to get is during the middle of the day, and so they would like to have some storage devices that will help them take care of requirements during the rest of the day as well as through the night. So, you have to put a combination together when you work with such devices. So, these are a whole bunch of parameters that work together that we have to be aware of when we try to build solar energy based systems, and I think that gives you a broad overview of these circumstances. So, as we look at as we look forward into greater detail on what is that solar radiation, how we can tap it, etc. These are the kinds of aspects that have also to be looked at when you try to deploy it as a technology. It is nice to do something in the lab. In the lab we are going to look at how they test these things in the lab and what circumstances they put the lab conditions on the experiment. What you will see is that real life circumstances are what you saw today in the class today, and so from those lab conditions, when you want to make a when you make a product, let us say you open a factory to make those solar panels and put it out as a product, from your test conditions in the lab you have to account for these real life conditions in the real life circumstances for it to be a successful product, and that is the perspective that you need to have, and that was the purpose of today's class. Thank you.